with the goodness of fit. Last year, the annual bird count at the La Reserva was given this distribution. This year, of the 1,330 birds counted, 324 were robins, 165 were finches, 100 were blue jays, and the rest were other varieties. So first of all, I would like you to pause the video and think about how this question is different to the chi-square model. Welcome back. Hopefully you realise this is comparing two things together which are already given in the question. We're going to compare a sample and the distribution. So let's have a look. We're going to call these observed and expected. Now, if we have a look at the question itself, this is the key bit of information here I've highlighted in yellow. Now, our observed in this instance is going to relate to the particular sample. So what I'd like you to do is, when you take a note of these things, put your own notes next to each of these words. So observed relates to the sample. The sample is an example of the whole, and it doesn't represent the whole population or what we'd expect from the whole population. Now, the expected is something you have to manually calculate. Now, here comes another difference to the chi-square model. And the reason why is because in the chi-square model, we use matrices. And in this model, we're going to have to manually calculate something. So we have to be able to get from 324 to 332.5. Well, the way you do that is by using each of these percentages. So what you do is you take the 25% for robins and change it into a decimal, 0.25 times by the total amount, 1330. And we're going to say the answer is 332.5. And then we'd repeat that process. So for this, we would take the 13%, which is 0.13, times by the total amount. It's going to give us 172. 7%, 0. times 1330. Can you pause the video and work out what the mistake is? Excellent. Hopefully you notice this should be 0.07 with an additional naught. And then finally, you could add all of these together and then minus it from 1330, but you could make a few mistakes, so it's best to repeat the process again, but this time with the remaining percentage as follows. So we have our sample in our experiment, and we have what we would actually expect based on the percentages. The questions are always going to look like this. Now, as before, it'll have very similar processes. The first thing you need to do is state your hypothesis. Your hypothesis is going to be different. However, you will have the null hypothesis, which is H0, and you will have the alternative hypothesis, which is H1. We will state that the sample agrees with the population distribution. That is the null hypothesis. This is always the same for these kind of questions. H1, we will write it does not agree. Next step, as before, is calculate the degrees of freedom. Now, when we're focusing on the degrees of freedom, we're just going to be looking at the observed table. Now, remember, degrees of freedom represent how much freedom we have if we put in bits of data. So say, for example, this data didn't exist. And I'm going to get rid of all this data here. If we first of all decide a value here is going to be 324, that's 1 degree of freedom. If we decide this could be 100, that's 2 degrees of freedom. And then we've got a choice of what this could be. This could be anything, as long as the maximum doesn't exceed the given maximum in the question. So if we say this is 741, then this must be 165. This is why we have 3 degrees of freedom, because there are 3 decisions that must be made before we can work out how to fill out the complete table. Another way of thinking of it is using the formula row minus 1 times column minus 1. But this is for a table which does have more than one row and more than one column. For the question above, we only have columns we're focusing on. So all we're going to do is we're going to take the column part of the formula, which is column minus 1, and substitute into that. So focusing on just the observed part of the table, we can see we have 1, 2, 3, 4 columns. So our degrees of freedom are 4 minus 1, which equals 3. Now I'm going to show you through a series of screenshots what we need to do. We need to input this data we've calculated here, which is the same as the data here, and we need to put it into the calculator. This is where another major difference occurs to the typical process. So using this data from the table, we are then going to write it in a vertical fashion. So if we were to write it in a vertical fashion, we'd get our table. Instead of observed and expected being the row headers, we're going to have these as the column headers. And we're going to just transform the data. So this would be 324, 165, 100, 741. You can hopefully see the pattern. And then we'd put 332.5 here, 172.9 here, 93.1 here, and 731.5 here. This data you then need to enter into the stat menu part of your calculator. We've done this plenty of times before, so I'm not going to go over it on the calculator. What you need to get up is the stats part of your calculator. So if you can pause the video and have a think about what we need to press on our calculator. Welcome back. Hopefully you realised we need to find the stat button and then we need to press edit. So the stat button is always going to be in the same place, which is this button here. And then once you press that, you need to press number 1 edit and you can change the list numbers. If you need to clear it before that step, you press stat, then number 4, which is clear list, and then you enter list 1 and list 2. Please let me know if you can't remember how to do that. You then put in the data on the left hand side, the right hand side, press enter. Please pause the video and try that now. Step 2. We're then going to do a similar thing as we did before. We're going to go on to the distribution menu, and the distribution menu can be found near the vars button. So let's have a look at that. On my calculator, and you should have your calculator in your hand as well, we're going to go on to the distribution menu. But this isn't quite right, because the distribution should be used for normal and binomial. So instead of the distribution, we're going to go back to the stat menu. So the stat menu is here. We're then going to go across to tests, and then we're going to go down this time to the goodness of fit test. So you're going to go to option D, where it says chi-squared GOF test. Press enter. Observed will be L1. So it will look like this now. Expected L2. You need to make sure you put in the correct degrees of freedom, which we've talked about, and then you need to press calculate. Once you've done that, you are going to get these answers. Chi-squared, P, degrees of freedom, which you've already entered. Now we are going to analyse these. We're going to analyse these in the same way as before. We are going to compare the chi-squared goodness of fit value, which is 1.213, with this value, which is 7.815. Now, going back to the question, the critical value was given to us in the question. So we are going to take these two numbers, this number here and this number here, and we need to put an inequality sign between them. 1.213 is smaller than 7.815. Therefore, we can say that the goodness of fit, or the chi-squared value which is associated with the goodness of fit, is going to be smaller than the critical value. This process is the same as what we did before, because the rejection and the acceptance policy is exactly the same. So because this chi-squared value is smaller than our critical value, which is given in the exam, we need to accept HO, because what this means is that as this value, our chi-squared goodness of fit, is smaller than our critical value, we must accept HO, which means we reject H1. This means that our data is quite similar. So if we go back to our original data in the original table, we would see there's a similarity between both our observed and expected. They're so similar, in fact, that it's nothing out of the norm we wouldn't expect. So therefore we need to accept the null hypothesis.